Today we're going to study the capacitive load. So let's see if we have a power supply. This is an alternating current supply. And then we have a capacitor. Okay. Now let's see the current. The current goes back and forth. So we put here IC. Now the voltage across the capacitor, okay, we call it VC. This C stands for the capacitor, is equal to the amplitude, so I put here VC, and then I put sine omega t. Okay, so the reason I put sine again is because if t equal to 0, I don't have any voltage. The voltage is equal to 0 at time t equal to 0. So I have this situation. I do a plot. Okay, so I put here, this is VC, and then this is the time t, and then at time t equal to 0, VC is 0, so I start here at 0, and it's sine wave, so I go like this, come back, and here is one wave. So now we need to see what happened to the current. So the voltage, we have its equation. Now we need to know the equation for the current. We know from the capacitance that C is equal to Q over V. This is we know from the capacitance. This is a formula for the capacitor. Now Q, I put here Q is equal to CV. Now Q is equal to CV. So I can put here Q, this is the charge in the capacitor, is equal to C, and then I put here, I can put VC. QC is equal to C, this is the capacitance, and VC, this is the voltage across the capacitor. So now I take this VC, I have it here, so I put here QC is equal to C, and I put this VC. This VC is the amplitude, I put it here. You see, VC is that one, is the amplitude of the wave. And then I put here sine omega t. Now I need to take a derivative of Q to get the current. So we know that the current I is equal to dQc over dt, which is equal to C. This C is constant. Remember, C depends only on, I put here C is equal to A epsilon 0 over D. This D is the distance between the two plates. A is the area of the plate, and epsilon 0 is the permittivity of free space, which is constant. So this is constant. VC is the amplitude, is constant, so I put here VC. And you can see here, I have the sine. I have to take the derivative of sine with respect to time. So I have to do the chain rule. So omega should come out. And we know the derivative of sine is cosine. So I put here cosine omega t. Now, if you pay attention to this equation, look at here. I have a current. Okay, I can call this current IC if I want to. This is the current through the capacitor, and that goes through the capacitor. This is the capacitance, magnitude of the voltage, omega cosine omega t. Look at here, I have IC here, and then I have this thing here, a new thing that shows up. What is this? Remember, this doesn't have a unit. So, and this one has a current, unit is amps. So this gotta be a current. So this is actually is IC. This is I, the amplitude of the current. So let's do this. IC is equal, I put C omega, and I put VC. Now let's pay attention to this equation. This is the voltage. This is the current. So this gotta be a well, gotta be the inverse of a resistance. Let me put here VC is equal to 1 over C omega times IC. So this here if you look at Ohm's law, what is Ohm's law? V is equal to Ri. This is Ohm's law. Okay? So V is equal to some resistance times the current. So this is called the capacitive reactance. This is capacitive reactance. They don't call it resistance because they want to mix it with this R, so they call it reactance. So this plays a role of some resistance, but this resistance depends on omega, depends on the frequency. So I can put here, they call it XC. So I put here XC, this is the reactance for the capacitor, or the resistance if you want. 1 over C omega. Okay? This XC is equal to 1 over C 2 pi F. Something interesting happens here. C is constant, 2 pi constant, F is variable. So if the frequency is so high, the resistance or the reactance goes to 0. So if the frequency of the cycle is so high, this capacitor will play a role of a wire. It's like a wire. So it's not gonna affect, it will play the, because when the reactance will become 0, it means the resistance 0 is like a wire. Okay? Now, if the frequency is low, then you have a higher reactance. So if you go low frequency, then the capacitor will react to that alternating current. But if you go very high frequency, then it becomes like you don't have a capacitor, you just have a wire, like that. Okay? Now, we need to look at this equation. We need to go back here. I put IC. I need to go back to this equation. You see that one? I have IC. I told you this is IC, capital IC amplitude. But the cosine omega t is equal to sine omega t plus 90 degrees. You see? If you, let me adjust a little bit. Okay, so you can see that. So I have IC is equal to the amplitude sine omega t. Now, what's happening is I have this 90 degrees because I know that if I go here, sine omega t plus 90 degrees, this is equal to sine omega t cosine 90 plus sine 90 cosine omega t. I put plus here. This plus that. Cosine 90 is 0, so it goes away. Sine 90 is 1. So cosine omega t is equal to sine omega t plus 90 degrees. So instead of putting the cosine here, I can put the sine with 90. So now, look, let's look at the voltage here. This voltage is variable. This is amplitude, and I have sine omega t. Here I have a current, amplitude, sine. So I have sine, but I have 90 degrees. So what happened in this situation is the current and the voltage are not in phase. There is a 90-degree difference between them. So what we need to do, we need to look at the phasors, what's happening to the phasors. So I go up here, okay, and then I draw the phasors. Let's draw the phasor for VC. So the VC, the voltage, this is the voltage here. I put here VC, and then here, this is omega t. This is the angle theta omega t. So when VC is changing, this phasor is rotating. I told you, if you look at one video before, I have 4 quadrants, 1, 2, 3, 4. So this is the first quadrant, second, third, forth. So when the wave is going like that, the phasor is rotating. Now, let's do that for the current. Okay, so the current is advanced by is kind of the angle here for the current is 90 degrees plus omega t. So I have to add 90 degrees. So what I do, here is the current. I put here IC. And here is 90 degrees. So the phasor, okay, the angle between the phasor for the voltage and the phasor for the current is 90 degrees. So the voltage and the current, they don't come to the capacitor at the same time. They don't come there. Let's see, for example, their peak doesn't come at the same time. Let's look at the peak of the current. Okay, so at time t equal to 0, I have sine 90. Look at this equation here. At time t equal to 0, sine 90 is 1, so I have the amplitude. So let me put the current here. This is IC. Okay, so what happened is, let me put this point here, then this one, then this one, and this one. So the current at time t is equal to 0, I have maximum current, because at time t equal to 0, I have sine 90 times IC, this is the amplitude. So I have maximum current, so I start here, and then I come down. Okay, now what you see is when the voltage is high, the current is low. So when the current is low, the voltage is high. Let's look at here what's happening to the voltage. The voltage now is 0. The current is high, but it's going the other way, like that. Now let's look at here. The voltage is high, negative high, but the current is 0, like that. Let's come over here. The voltage is 0, the current is high. So look at the peak of the current and look at the peak of the voltage. They don't come, look at the time here, they are not at the same time. They don't come to the capacitor at the same time. They come at different times. There is a phase difference of 90 degrees. So this is 90. If you look at, we have 90 here, we have 90 here, and then we have 90. That's give us 4 times 90, 360. So this is a 2 pi, which is 360 degrees. So you can see that the current and the voltage are not in phase. Okay? They are not coming together equally to the capacitor. Now, one thing I want to mention about this reactance here. Like I said, for Ohm's law here, the resistance is constant, okay? Unless you increase the temperature or so, then this resistance starts to change differently, change, okay? Now, for here, I don't have to do anything to the temperature, it's just the frequency. If I come over here, change the frequency, you get different reactance. So the resistance of the capacitor changes with the frequency.